Good morning, friends. Yesterday we have seen the brief details of the semiconductor diode. Today we shall see we shall have the brief discussion about what yesterday we have discussed. Yesterday we I gave the comparison between diode and resistor. As you know, the diode is a non-linear device, whereas a resistor is a linear device. The diode, in fact, it is two-terminal device unlike the resistor, but however the diode cannot conduct in either direction. It can only conduct in only one direction, whereas the resistor can conduct in both the directions here. And also we have seen in the construction, the semiconductor device consists of the mainly P device, that is what is we have here, and the N device on your right side, and the in P type the holes are the majority charge carriers, whereas in the N type the electrons are the majority charge carriers. And you can see here the terminal that is connected to the P type, it is called as anode, and whereas the terminal that is connected to the N type, it is called as cathode here. And in between this P and N layer, you can see that there is a layer that region, it is called as the depletion region. This is the region where which is depleted of the free charge carriers. It only contains the fixed immovable ions. So and depending upon this depletion region, so we will have corresponding barrier voltage. So as you know that, and also we discuss about how the depletion layer is formed when there is no battery connection, so under no bias conditions, you can see that the holes will move from the P type to N type, and whereas the electrons will move from the N type to P type here. And therefore, so what happens, so finally because of that movement, what happens, when these holes move to N type, they neutralize the electrons. Similarly, the electrons, when they move from the N to P type, they neutralize the holes, and therefore that creates only a layer or region consisting of the immovable, that is the fixed ions here, and therefore a depletion region is formed. And this region is it is also called as emptied region or depleted region, because this region, it is depleted of the mainly the. So here you can see that the barrier potential corresponding to this barrier voltage corresponding to the particular depletion region here. So, and also we discuss about the forward biasing of the semiconductor diode. Forward biasing means whenever the mainly this when this anode, it is connected to the positive terminal of the battery, and cathode, it is connected to the negative terminal of the battery, there will be a repulsion between the positive terminal of the battery, therefore the holes as well as the electrons, they move away from the particular positive and negative terminal, and therefore what happens, the depletion region decreases. So therefore correspondingly what happens, the barrier voltage will decrease here. And finally after a certain time, there will be a free flow of current or free flow of the charge carriers from the P to N type, that is the conventional current, that is what is we have told about. And also we discussed about the reverse biasing. In case of the reverse biasing, you can see that the this particular in case of the reverse biasing, anode is connected to the negative terminal of the battery, whereas cathode is connected to the positive terminal of the battery here. So when such thing happens, the holes from P region will be attracted to the negative terminal. Similarly, the electrons will be attracted towards the positive terminal of the battery, and therefore what happens, this depletion region it will increases, and correspondingly what happens, the barrier height, or what you can say that the potential barrier that exists because of the depletion region, it also increases, and that will block the the movement of the charge carriers across the junction, and therefore only the diffusion current will be 0, whereas the drift current, which is due to mainly the minority charge carriers, will flow, and this drift current it is in the range of microamperes. And also we have mainly discussed about the VI characteristics. So VI characteristics of an ideal diode as well as the VI characteristics of the practical diode. You can say that here in case of the VI characteristics of ideal diode, you can see that, so for V lesser than the 0, the current is 0, so therefore you will get this particular characteristics. For V equal to 0, the current will be infinite, so therefore you will have the two region, only one is called as the forward bias region, another is reverse bias region in case of the ideal characteristics, because ideal the ideal VI characteristics in this case, in forward bias, the diode acts as an open circuit, whereas the short circuit, and current flows, whereas in reverse bias the diode acts as a open switch, and therefore the current flowing through it will be 0. When it comes to this, if you look into the VI characteristics of the practical diode, you can see that it consists of three regions. One is the forward region, another is the reverse region, and third region is called as the breakdown region. If you here if you have a look at the forward region, until the forward voltage reaches the cut-in voltage, that is called as threshold voltage, current until that point the current will be 0, and once the forward voltage exceeds this cut-in voltage, so what happens, the current increases. And similarly you can see that in the reverse region, the current is very small current will be flowing, that is between 0 to minus VZK, and it is of in the range of the microamperes, whereas the breakdown region, that is for the region for voltage greater than minus VZK, you can say a large current will be flowing through the diode, and which may damage the diode here. So these are the few, I think, points we discussed. Apart from this, and apart from this, mainly we also discuss about the approximation, diode approximation. There are three types of diode approximation. This is the first type of the diode approximation. Here you can see that the first type of the diode approximation, that is in this case you can see that the diode either acts as the open circuit or closed circuit. Whenever the diode is forward bias, the diode acts as a closed circuit, that is closed switch, and if the diode is reverse bias, it acts as an open switch. So in the first diode approximation, diode is either represented either as an open switch or closed switch, and this particular diode approximation is being used mainly to troubleshoot whether that is to test the diode is conducting or not conducting. In second approximation of the diode, you can see that the diode is represented by a switch in series with a 0.7 volts voltage drop, and here whenever the diode is forward bias, the switch will be closed, that will be in series with the 0.7 volts battery, and if the diode is reverse bias, the switch will be it will be open, that will be in series with the 0.7 volts drop. And this particular diode approximation, it is mainly used to find out the load voltage and the load current, whereas in third diode approximation we have seen that the diode is represented by the switch in series with 0.7 volts drop in series with the bulk resistance. Once again, here when the diode is forward bias, the diode is represented by the closed switch in series with the 0.7 volts drop, and which is in series with the RB here. Whenever the diode is reverse bias, it is being represented as open switch, which is in once again series with the 0.7 volts in series with RB there. And also we discussed about some of the diode parameters. So if you look into this, we have discussed the 4 parameters. One is the VR, that is defined as the maximum value of the reverse voltage that can be applied to the diode. If the voltage, reverse voltage exceeds this VR value, then diode must be, the diode will get damaged. Therefore, this VR, it is defined as the maximum value of reverse voltage that can be applied across the semiconductor device. Whereas second parameter what we defined is IR, which is called as the maximum allowable reverse current that can flow through the device, right, when the device is reverse bias, right. And also we discussed about, we defined okay, the forward current. This is the forward current that can be allowed to flow through the diode when the diode is forward bias. Apart from that, we have got one more the parameter, that is the rating, that is called as FM. This represents the maximum switching frequency of the diode. So now let us look into mainly today we shall discuss about okay, some aspects of the diode, the operating point. At the end of this topic, the students will be able to understand the concept of operating point, that is also called as the Q point, that is nothing but the quiescent point. We shall see why the operating point is called as the quiescent point, so and all that. And also we will come to know, right, how to find out the DC condition exists in the diode circuit. So we have considered here one simple okay, diode circuit involving the mainly this particular okay, and you can see here. So we have a mainly so you can see here we have a DC power supply in series with a resistance R, which is in series with a diode D here. Okay. So therefore here you can see that the anode is connected to the positive terminal of the DC supply, whereas cathode is connected to the negative terminal of the DC supply. Therefore diode is forward bias here. Okay. And so therefore if you apply KVL to this, we will get this equation, wherein that is using Kirchhoff's voltage law, the VDD okay, you will be equal to I into R plus VD. So I is nothing but the current flowing through this resistance, and IR is nothing but the voltage drop across the resistance here, and VD is nothing but the voltage drop across the D, and whereas the VDD is the applied DC supply voltage here. So this you can assume it as equation 1 here. So and you know that the characteristic equation of the diode is given by I equal to Is into e raised to V by eta, that is n into Vt minus 1. This is, you can assume it as equation 1, where here you can see that the Vt is thermal voltage, whereas n is the number, usually it can have either 1 or 2, and in general n is assumed to be 1, whereas Is is called as the reverse saturation current. So assuming the n, Is and thermal voltage, right, are known, we have two equations for two unknown quantities, that is one is Vd and other is I, that is current flowing through the circuit here. So if you substitute equation 2 in equation 1, we will get the following equation, wherein Vd is okay, defined as Vd equal to Vdd minus Is into R into e raised to V by n Vt minus 1, right. So this equation, which is a transcendental equation for the VD. So the transcendental equation means usually the equation consisting of the exponential terms and some trigonometric functions are called as transcendental equations, and usually there is no simple analytical solution this particular equation. Then how to solve this circuit problem, how to find out the solution to this particular equation. So there are plenty of methods are available to find out the unknown quantities. One, maybe there are 5 techniques that are being used. One is that is using the simulation packages such as SPICE or Agilent's advanced design system ADS, and it may be the second technique that is being used is called as the numerical method, such as using making use of Mathematica, the software tools such as Mathematica or MATLAB or the MathCAD, etc. And also, right, the third technique that is being used mainly to find out the solution to the earlier problem is iterative analysis. The fourth technique that is being preferred to find out the solution for the earlier problem is approximate analysis, and the last among this is called as the graphical analysis. So this is today's this one in the lecture we shall discuss about the graphical analysis, and using graphical analysis how you can find out the DC condition exist in the diode circuit. Friends, the first step you need to begin with the diode VI characteristic curve. You can see that this is the V, that is along the x axis, and we have I along the y axis, and there is a non-linear relation exists between V and I, that is represented by the equation 2 there. And similarly, if you you know the equation, right, if you rearrange the equation 1 in terms of I, we get I equal to VDD by R plus VD by R. So if you compare this equation with the equation for the straight line, right, so as you know that the equation for the straight line can be defined as y equal to b plus mx. Here, where in this equation y and mx are the variables and b is a constant and m is the slope of the straight line here. So if you compare this y equal to b plus mx with this equation, above equation I equal to VDD by R plus VD by R, we get the 2 points here. We get a straight line, so that exists between VDD and VDD by R. So VDD along the x axis and VDD by divided by R, that is along the y axis. And please note that the slope, when you compare this, here as I told you that m is the slope of this straight line and m is nothing but the 1 by R. So that is the slope of this particular straight line here, and we call this straight line as the load line here. So as I told you that how to go ahead with this graphical analysis. Using graphical analysis, we are finding out the operating point, that is the DC conditions exist in the diode circuit. So we begin with mainly the diode VI characteristic curve, then we find out, right, by rearranging the equation in terms of I and comparing this equation mainly with the straight line equation, will get a straight line that is drawn between the VDD and VDD by R, and this line is called as the load line. So here you can see that now in third step we plot these two curves on the same graph. You can see that this is the straight line existing between VDD and VDD by R and having a slope of minus 1 by R, and this is whatever you can see here, that is nothing but the diode characteristics, and intersection of this, whatever you can see this intersection, that point we call it as the operating point. So corresponding to that operating point, whatever voltage is there, that is we call it as VD, and corresponding to this operating point, whatever current that is flowing through the diode, that we call it as ID here. So these are the DC conditions. VD and ID are the DC conditions, right, exist in the diode circuit corresponding to this operating point. So this is how, right, graphically we can able to find out the operating point or operating conditions of the diode circuit. The point where these curves intersect, okay, is a simultaneous solution to equations 1 and 2. The graphical method is impractical solution method for all but simple circuit. That means this particular graphical analysis or graphical method, it can be used only for simple diode circuit, but we cannot say that this will be the solution for all problems. So however, this graphical analysis, it is being useful for qualitative understanding of this circuit. That means, right, when what happens when VDD increases? Friends, you can see here, okay, you can note on that, okay, this whatever line you can see, the blue color line, that is the VI characteristics of the diode, okay, whereas whatever the red line that you can see, that is nothing but the load line, having a slope of 1 by R. Whenever the VDD increases, what is happening? The operating point, that is the intersection point, right, it also increases here. So that way we, by increasing, right, VDD, what is exactly happening in the diode circuit, that can be noted from this particular graphical analysis technique. And also it could be, the other solution could be, whenever the load resistance increases, what is happening here? Once again, here the operating point, that is the junction point, okay, interjunction point between the VI characteristics and the load line, that will also, goes down, it comes down. So such type of qualitative analysis can be done, right, using the graphical analysis technique. Okay. A load line is used in graphical analysis of nonlinear electronic circuits. That means the nonlinear electronic circuit means the electronic circuits containing nonlinear devices, right? And friends, we know that diode is one of the nonlinear device having nonlinear VI characteristics. Similarly, we have a transistor also, right, behaves like a nonlinear device. So this particular graphical analysis or DC load analysis, it is also called as DC load analysis. It is being used mainly, mainly to represent the constraint, right, other parts of the circuit placed on the nonlinear device, like a diode, or it could be transistor here, and it is usually drawn on the graph of current versus the voltage in the nonlinear device, called the device characteristics. So first we draw a load line between VDD and VDD by R, so that represents a straight line, and then so we draw the VI characteristics of the nonlinear device. In this case it is diode, and therefore this load line, okay, usually a straight line, it represents what the response of the linear part of the circuit. That means here the load line means it represents the resistance R, that is called as the load here, and this load, it is connected in series with the nonlinear device. In this case it is diode. The points where the characteristic curve and the load line intersect are the possible operating points. So therefore this operating point, okay, so it is also called as the Q point. What is Q point? Q means it is nothing but the quiescent point. Quiescent, the meaning of quiescent means silent, that is in the that represents the absence of AC voltage. It only represents the DC conditions exist in the diode circuit. So therefore corresponding to Q point, whatever condition exists, that is VD and ID, so these are the DC conditions existing in the diode circuit. Okay. So now let us take one example here. Okay, we have a DC supply and in series with the load resistance, and which is once again in series with, okay, a diode. Okay, this particular VDD, this is defined as VDD. This is nothing but 5 volts, whereas this is the R. So the value of R is nothing but the 100 ohm, and this will be in series with a D, So whatever voltage drop is there, we write it as Vd, and this is whatever voltage drop is there across the R, we represent it as Vr, and whatever the current flows through this resistance, or that is called as the mainly the current I. So here you can see that this is a diode anode, and whereas this part is called, this terminal is called as cathode, and anode is connected to the positive terminal of the DC supply, whereas cathode of the diode, semiconductor diode, is connected to the negative terminal of the DC supply. So what happens? The diode is forward bias. So when diode is forward bias, so what happens? This equation, it looks like, so if you draw the equivalent circuit, so this particular circuit, it looks like, right, having a DC supply, right, then in series with a resistance, and then we have got a conducting diode here, and this is nothing but VDD, so which we have, right, given value of the VDD is 5 volts, whereas this is nothing but a series resistance whose resistance value is 100 ohm, and this is the current flowing to this, and voltage drop across the resistance, it is represented as VR. If you apply KVL to this, so Kirchhoff's voltage law, so what we will get? The equation will be VDD, that is your, what we are assuming is that, so this acts as a, instead of short circuit, it acts as a, it provides a small DC supply, that is called as VD, that is voltage across the diode. So therefore VDD will be equal to I into R plus VD. So this is the equation we get. First, to get a straight line, what we do is to substitute I equal to 0. When you substitute I equal to 0, so what we get? We get mainly VDD equal to this result in 0 plus VD, and therefore this implies, what it implies? So VD, that is voltage drop across the diode, will be equal to the VDD. So therefore, so one point we get, that is, we call it as point A. So point A, that corresponds to I equal to 0 and VD equal to VDD, that is nothing but how much? So that is given as 5 volts. So therefore I can straightway mention it as 5 volts. So this is the one point we'll get here. The other point could be giving, if you substitute VD equal to 0, so substituting the VD equal to 0. So on this equation, what will get? So VDD will be equal to I into R. This is equal to nothing but VD. So sorry, this will be 0. Therefore, what happens? I will be equal to VDD by R here. That is nothing but VDD is given. VDD is 5 volts. So what is the resistance? It is 100. So this is nothing but the 0.05, or you can say it as 50 milliamp is current. So therefore I will get one more point, that is called as extreme point of the DC load line, that is point B, which corresponds to the VD equal to 0 and the I equal to 50 milliampere. So there are 2 points here. Now let us look into these 2 points. So using the right, first, as you know that in the graphical analysis, mainly we need to draw, okay, this is represents the V axis, this is current axis, and this is nothing but you can it as 10 milliampere, this is 20 milliampere, and this will represents 30 milliampere, this represents the 40 milliampere, and then finally we have 50 milliampere. Correspondingly we will have right 1 volts voltage, that is diode drop, then 2 volts, 3, then okay 4 volts, then 5 volts. Okay, if the diode characteristics, okay, okay, it is looks like this point here. This is the diode characteristics what you are getting, and the DC load line point, that is point A, that is along x axis. Okay, therefore I is 0 and Vd is phi, that is this point. This point we call it as the point A. Okay, the point A represents the current I equal to 0, and Vd phi, that is voltage drop across the diode, is nothing but 5 volts here. Similarly, point B is nothing but what, the Vd is equal to, right, corresponding to Vd equal to 0. Corresponding to Vd equal to 0 means this is this axis. So therefore the point will be here. So this is called as the point B. So if you draw the straight line, if you okay, this is the DC load line, or you can call it as load line. So this will be the VI characteristics of the semiconductor diode, whereas this whatever straight line, right, I have drawn, okay, so that is represents the load line. Then the extreme points of, right, this load line is, one is point A, that is representing I equal to 0 and Vd equal to 5 volts. Similarly, the other extreme point is point B, that corresponds to Vd equal to 0 and I equal to 50 milliampere, right. So then whatever intersection that is taking place between this load line and the VI characteristics and this point, we call it as the Q point. And corresponding to this Q point, whatever voltage exists, that is how much we will get. This we get it as volts is, okay, that is Vd, that is nothing but 1 volt, okay, and corresponding to this, you can see here it is approximately somewhere, okay, you will get between, that is Id, that you will get it as 45 milliamp. So this Q point, so it represents, okay, the operating point of the diode circuit, right. Corresponding to that operating point or Q point, the whatever voltage we have, that is called as Vd, that is nothing but the 1 volt, and corresponding to this point, right, we extend that point along the y axis. So that gives the diode current, that is current flowing in this circuit here. So accordingly we will get the Q point, and this Q point is nothing but the operating point, which represents the DC conditions, okay, existing in the diode circuit. So if you have a look at it here, here what the simple diode circuit what we consider, right, and is having a DC supply of, right, 5 volts in series with the resistance R. The resistance value is 100 ohms, whereas the voltage drop across resistance is called as VR, and which is in series with the Vd, that is the diode. Okay, so as I told you that the anode terminal is connected to the positive terminal of the battery, whereas cathode it is connected to the negative terminal of the battery here, and therefore diode is forward bias, right, and therefore what happens here? So if you write it conducts, when it conducts, if you apply the Kirchhoff voltage law, we get VDD equal to IR plus VD. So therefore VDD is the supply DC supply voltage is equal to I, that is current flowing through the diode circuit, and R is the series resistance, and VD is the voltage drop across the diode. So first, to get a point A, what we need to do? We need to substitute I equal to 0. If we substitute I equal to 0, we get VDD equals to IR plus VD. So therefore this equals to, this is nothing but 0 plus VD, and this corresponds to what? The VD equal to VDD. So the given value of VDD is 5 volts, therefore VD is 5 volts. So therefore, okay, the point, if you can plot this point A on the diode characteristics at I equal to 0 and VD equal to, okay, 5 volts here. So similarly, the second step, what you need to do? You need to substitute the VD equal to 0 in equation for VDD. Therefore VDD will be equal to, okay, I into R plus 0, and therefore from this what you can derive, I is nothing but the VDD divided by R, and the VD is given, VDD value is 5, and therefore divided by 100, this is corresponds to 50 milliampere, right? So therefore you have to plot point B on the diode characteristics at I equal to 50 milliampere and VD equal to 0. If then using these 2 points, point A and point B, you can draw the straight line that which represents the DC load, and therefore this is called as DC load line, and therefore intersection of this DC load line and VI characteristics of the diode, it will provide the intersection point which is called as the Q point. From the Q point you can note on that ID comes approximately, that is equal to 40 milliampere, and VD you will get it as 1 volt here. So these ID and VD are called as the DC condition. So therefore here you can see that, okay, this is whatever you can see here, this is nothing but the VI characteristics of the diode, and this straight line, this is nothing but the DC load line, okay, representing the DC load here, and intersection of this DC load line and the VI characteristics of the diode, it will provide one intersection point that is called as Q point, that is nothing but quiescent point. Quiescent point means it is the meaning of quiescent is the silent, okay, that is in the absence of the AC signal, whatever DC condition exists, so that is represented by the Q point. Therefore corresponding to Q point, you can take this you can extend this Q point along the x-axis, you will get VD equal to how much? 1 volts. Similarly, if you extend this Q point on the y-axis, you will get ID equal to the 40 milliampere. Therefore, so from Q point you will get ID equal to 40 milliampere and VD equal to 1 volt. So which are called as